meeting is being recorded.
So today we're starting with chapter 8. Previously we were working with chapter 7, where we discussed work and energy. Essentially, we defined work to be the quantity that is non-zero if the force can make a displacement, so it has an impact on the motion. Then we say work is done by this force. And then we said to do work by a force, we need to spend some energy, so we defined the kinetic energy. We said the kinetic energy is the energy associated with motion, and then we related these two because to do work we have to spend some energy. Then I can write the net work done on an object is equal to the change in kinetic energy of this object, where K is half mv squared, as we said before. Today I'm studying a different type of energy. I'm studying energy which can be stored and converted energy or used to make motion. I'm naming this stored energy the potential energy of an object. So an object can have some kind of stored or potential energy, which it can later convert to kinetic energy and move accordingly. I'll give you a simple example, which is you carry a ball at a non-zero height. Let's say you carry it at a height of 10 meters, you release this ball and it immediately falls down. And you say it falls due to the pull of gravity, right? And as it falls, it gains more and more kinetic energy. V increases because essentially you have some acceleration. From kinematics, we expect the speed to be increasing. From an energy point of view, what's happening here, I can also describe it in terms of energy. There was some stored energy in the ball. Once you release it, its speed starts increasing from zero because it was like fixed at this height. Once you release it, its speed starts to increase, and basically some stored energy is being used and converted to kinetic energy. So we're talking about this stored or potential energy today, and we'll also be talking about some conservation of energy, which is basically this transformation which I talked about, where the potential energy can be converted to kinetic energy, and it actually can be the other way around too. So you can see here some forms where I can store energy. I talked about one of them, which is when you carry a ball on zero height, you release it, it immediately falls. Same thing here with the weights. They are at a non-zero height. Once you release them, they immediately fall down, which means they had some stored energy in them. I can see stored energy in other forms as well. Batteries store electric energy, quite simple. Here, also, the bow actually gives some stored energy to the arrow. Once you release the arrow, it moves, it converts its stored energy into kinetic energy. Spring systems similarly store some sort of energy. You can see this sinusoidal function, this red graph that you see here. This shows how the stored energy is changing at different locations. At the maximum displacement, just here, for example, the potential energy drops to zero. At certain points, the potential energy is maximum. We're gonna look at how these energies change in detail. Um, so as you can see here, essentially the potential energy, it can cause motion, but it doesn't exist when we have motion. Rather, it can exist when we have a certain position, such as putting the ball or the weights at a non-zero height, or a certain configuration, such as compressing the spring or putting some chemicals in the battery with an insulation between them. In this configuration, some stored electric energy can exist. So this energy exists when we have a certain height, a certain separation, a certain deformation, a certain arrangement. The object that is in these situations doesn't do any work, but has the ability to do so. And that's why I name it potential energy. It can be used to do work. Now, of course, in this In this course, we're interested only in mechanics. So the potential energy which I studied, which I showed you here in the slides, I will only study the ones related to motion, such as the ball, the spring, the weights at non-zero height. These can cause some kinetic energy, but I will not focus on stored electric energy or electric potential energy. This is what you can take if you ever take an electricity and magnetism course. But I wanted to show it to you so you can understand that it's not a stored energy only for a certain height. It can be due to certain chemical arrangements. But what we're working on today is essentially two forms of potential energy: the gravitational potential energy, which exists in any object at a non-zero height, just a second.
This meeting is being recorded.
So just as we had the work energy theorem, where we wrote delta W net to be equal to delta K, I can put a relationship between the potential energy and the work done. I can write the change in the potential energy to be equal to minus the work done. I'll show you why we put this negative sign. It's essentially because the stored energy will always contribute to negative work, because the stored energy, when it's being used, it's going to be decreasing. Positive work is done. And if it is decreasing, this should be a negative sign. So let me show you an example. I have a falling object. As the apple falls, gravity is doing positive work. We have talked about it before. We said the work done by gravity can be written as mg delta H with a minus sign, or I can write it as mgt, where d is the distance covered. So the work here is positive because both the weight and d have the same direction. They are downward, so gravity will be doing positive work. The potential energy, however, is being used to generate motion, so it is decreasing. So delta U should be negative. The potential energy is decreasing because it is used to do work. So I expect it to be negative. That's why I put delta U to be equal to minus W. You can see here another scenario. You throw a tomato upwards. As it ascends, gravity does negative work. So in the first section, in the upward direction of motion, here delta Y is up and W is down. So W does negative work. Now gravitational potential energy is going to be increasing. Why? Because this tomato is moving upwards, its height is increasing, and we said the gravitational potential energy is related to the height of the object at which it's existing. The higher it is from Earth, the higher the potential energy stored. So as the tomato ascends, gravitational energy is increasing. And notice how here W is negative, delta U is minus W from our relationship. So this will be positive. Notice how the physics matches with the math. Now in the descent, as the tomato reaches the maximum height and starts moving downwards now, in this case, the height is decreasing, So the stored energy is decreasing. So delta U is negative. On the other hand, gravity is supporting this downward motion because they both have the same direction. Gravity and the displacement have the same direction. So the work done by gravity is positive. And from the relationship, work done by gravity is minus delta U. This also matches with our conceptual analysis. Now, one thing I just want you to be aware, I talked about the work done by gravity and how it can be stored, increased, and decreased according to position, used like decreasing as we ascend upwards, and then at some maximum height, like the speed becomes zero, whereas the stored energy can become a maximum, and then this can be used when we descend back down. But I want you to just be aware that not all energies can be reversed. So not all energies make a change similar to the gravitational potential energy, where it decreases with as we go down, and then it increases back up as we go up. This is just a feature of gravitational potential energy, whereas other forms sometimes cannot be reversed. I want you to focus on heat energy in particular, which we can encounter a little bit in this chapter because we see it as lost energy. As the block in the figure, for example, slides down, gravity does positive work and potential energy decreases. Let's say the speed here is downwards. So let's say the block goes from point A to point B here. As this block moves downwards, from A to B, the work done by gravity is positive, and U is going to be decreasing because the height is decreasing. So the potential energy is decreasing. However, during this slide, I want you to notice something that happens as well. If there is a frictional force, the friction will take part of the energy that was possessed by the object. Some of the energy, namely the potential energy, by the way. So here, the potential energy at A decreases as we go to B, and this energy is used to do work. Okay, we're doing some work between these 2 points, and this work is positive, but some of this energy is lost due to friction. So the friction which is exerted by the floor is going to slow down this block a little bit. It's not going to be sliding smoothly across the surface. So the result is some energy is lost due to the friction resistance to the motion, and this energy is seen in the form of heat. So now I can say, in fact, that the potential energy that the block had initially is going to be converted to, so that's one conservation law, which I can see. Look at the conservation law, which we will see more in detail with very good math in the future. The potential energy at A is going to be equal to the kinetic energy at B. I converted all of the potential energy at A into kinetic energy. Let's say the ground is here, so B is at a zero height. There is no potential energy at B. So the potential energy that was stored in the block at A was converted to a kinetic energy at B plus some lost energy due to heat. At A, we had 100 joules of energy. Then these are going to be converted into kinetic energies plus some lost energy. I would tell you, for example, the lost energy is 20 joules, then you can tell the kinetic energy at point A. We will talk more in detail about the conservation laws, but I want you to just see how the transformation happens in principle. But one important remark about the heat energy or the thermal energy is that the heat energy, unlike the gravitational energy, it cannot be reversed. So this block, which is at point, which has reached point B, if you reverse its direction up the incline, so if it goes back up, its potential energy will increase because the height is increasing, so it can store back some potential energy. Whereas the heat energy cannot be reversed, it cannot be taken back into the object. Like the object lost some heat energy as it descended. If it ascends back up, the energy it lost due to friction will not be given back to it. It will not be reversed, so not all energies are reversed. In particular, only potential energies can be reversed, which are the gravity and the elastic energies of the spring. Whereas lost energies such as thermal energy, they cannot be reversed, they cannot be taken back into the object. And that's a very nice feature of potential energies.
This meeting is being recorded.
So I wrote for you this nice relationship where I wrote U is equal to minus delta U. I can use that to put down a formula for delta U in terms of the equation of W. We took before the work done by a force is given by F dot delta X or F dot D, a scalar product of the force and the displacement. Let's write it as delta R. That's like the most general case, in case the motion is not along the x-axis. And we also wrote this as an integral of F dr or dx if the force is changing with position. We talked about this formula last time as well. So today I'll just write delta U in terms of this equation as well. So delta U, which is minus W, I can now write it as minus the integral of F dot dr or dx. So I'm gonna use this equation to start extracting some equations for potential energies. I will use this to derive gravitational potential energy equation. I'll name this UG, and elastic potential energy equations from the forces that cause them. So look at where I start with my study of gravity. So the gravitational potential energy, which is now minus the integral of the force dot dy. The force is gravity, so I'll substitute F by the gravitational force. I want you to remember something. This is a dot product. I'll have to account for the angle between the two, between F and the displacement. So if the object is moving upwards, then F dot dy is gonna have a negative sign between a 180 degrees angle between them, and the result is there will be a minus equation. So I put a minus sign here. If delta y is negative, this means we are descending, then this becomes a positive quantity. And the total change in potential energy is negative, which makes sense. So I put the equation of the force. I will integrate this over dy. Mg is constant. It doesn't depend on y at all, so I can take it outside the integral. And what remains is the integral of dy only. I can solve this integral and get y simply, which changes from y initial to y final. So the potential energy, the gravitational potential energy has a nice formula now. Delta is equal to mg times delta y. Again, notice how the physics would match with the math. If y is increasing, so the object is ascending, then delta y is positive, then delta u is going to be positive, which makes sense. An object that is ascending will have an increasing gravitational potential energy. And the other way around matches as well. And one other thing I want you to notice here, a very important conclusion, the gravitational potential energy associated with a particle Earth system depends only on the vertical position of the particle, not the horizontal position. Look at our formula. The change in gravitational potential energy depends on the vertical position. What does this mean? If I know I don't have a change in vertical position, there is no change in the gravitational potential energy. So I'll give you some scenarios. If we go from point A to point B here, delta U from A to B is simply 0 because there is no change in height. But if I go from B to point C, which is over here, delta U from B to C is going to be negative in this case because the object is descending, Y is decreasing. And if you take from C to some point D here, delta U from C to D will depend only on this vertical part, by the way. And that's actually the same as BC. So delta U from C to D is the same as from B to C because they have the same vertical change in position. So my important comment here is U, G, the gravitational potential energy, is independent of the path taken.
This meeting is being recorded.
So we can take a look at this nice example. We have a 2 kilograms block of slippery cheese that slides along a frictionless track from point A to point B. The cheese travels through a total distance of 2 meters along the track and a net vertical distance of 0.8 meters. So the distance that it actually covers is 2 meters. This is basically this distance. The net vertical distance is 0.8. So between this point and this point, the vertical displacement is 0.8. How much work is done on the cheese by the gravitational force during the slide? So the work done, I can write it as minus delta U which is going to be minus mg delta H. I can use the general formula for the work done, but my problem is, well, take a look at D. D is continuously changing in direction, so I'm not sure what angle to take. If I use the other formula, this one, then all I have to look at is the change in the height. So I'll write this as minus 2 kilograms times 9.8 times delta H, the change in the vertical height only, which is 0.8. Problem solved. I want you to see how the problem here approaches the question. What the problem does is, rather than directly looking at delta H, they say, let's consider that instead of going from A to B, we go from A to C horizontally and then down to B. And that is okay because like the gravitational potential energy is independent of the path. What matters is the initial and final points. And then the work done from A to C is 0 because D is horizontal and mg is vertical. So the angle between them is 90. And from C to B, D is vertical, mg is also vertical, so there is work done. You find the work from C to B, which is going to depend on this vertical height again. You get the same answer as the one I got. Mine is simpler to look at. Let's now take a look at the elastic potential energy. So we talked about the gravitational potential energy. This is the energy stored due to the gravity of Earth. We found an expression for that from the work done by gravity. I will now make a similar study of the elastic potential energy, which is the energy stored in a spring. I remind you the force that is involved is the spring force. A spring pulls or pushes objects if it is compressed or elongated. The force that the spring exerts has this formula. F equals minus kx. So if you bring a spring, it's just there at rest at its natural length. You pull this spring and attach a block there. The spring, once you release the block, the spring will move back to its natural position. It will pull the block inwards because it was elongated outwards. So delta x is out, half of the spring is in. So the spring force is opposite to the displacement direction. So I can first try to like find a formula for the spring force. It will be equal to the opposite of the elongation of the spring. And the more you elongate the spring, the more spring force there will be. And there will be an effect of the material of the spring itself. If the spring is very stiff, it will make a stronger force from the smallest elongation. Whereas if the spring is soft, it will make less force. So the stiffness of the spring is described by this constant K. So the spring force is equal to minus a constant, which is usually given to you, times the displacement of the spring or the elongation or compression of the spring. I will use this formula of the force to extract a formula for the elastic potential energy stored in the spring. Namely, I have delta U is equal to minus, so like we said, delta U is minus the work done, which is equal to minus the integral of F dot dx. My force now is the spring force, which I wrote as minus kx or minus k delta x. I will integrate that. One thing you notice here is the spring force does depend on position. It will not go all of it outside the integral as we saw for the weight force. Rather, only minus k will go outside. There's a minus there already, so I get k outside the integral. And I will integrate over x dx. The integral of x is x squared over 2. So I put the half outside. And this will vary from x initial to x final, from wherever the spring was to its final position. So I get this formula for the change in the elastic potential energy of a spring system. It is going to be half k x final squared minus half k x initial squared. And because this is a change in elastic potential energy, I can deduce that this is basically U final minus U initial. So U, the stored energy in a spring, is equal to half k x squared. That's a very nice formula. What is it telling us? You have a spring of stiffness K. You pull it by a displacement X. You stretch it by 2 centimeters, let's say. So this is elongation or compression. Then it will store some elastic potential energy, which is going to be equal to half kx squared. Let's check an example. This is another example on gravitational potential energy, by the way.
This meeting is being recorded.
So let's take a look at this question. I have 4 situations. 1 in which an initially stationary block is dropped, and 3 in which the block is allowed to slide down frictionless ramps. Rank the situations according to the kinetic energy of the block at point B greatest first. Rank them according to the speed at point B greatest first. So as a first impression, one would think that the first situation where the object is dropped from A to B just vertically in a free fall without having a surface at all would result in a higher speed, whereas sliding down over an oblique direction will result in less and less speed as we go, especially in situation 4 where the object dips down and then moves up. But look at how the math fixes our intuition. I know that the gravitational potential energy here is what is causing the motion. Here, delta U decreases from A to B because we are descending essentially, and it is converted into some work done. And this work
Professor,
is, yes.
the work.
This meeting is being recorded.
Okay. Elisa, can you help us further? Can you look at delta U between the different cases? I remind you of the definition of delta U. It is mg delta H. Is it more in the first, the second, the third, and the fourth situations, or is it like the same? Essentially, delta U depends on the change in the height.
For the third is like the two red dots, then the fourth one is the other red dot, right? At B.
So the third case is this: when you slide over this less steep
Oh,
incline. This is the third case, and the fourth case is when the object dips down and then moves back up to
the
point
block
B.
is still on the same axis.
So the block is moving at an incline here.
Yeah.
Yeah, and here it's gonna move down and then back up.
No,
What
the
do you notice
other
about delta? Huh?
delta U remains the same.
What remains the same? Can you repeat?
Delta U, because
Ah,
they remain
yeah,
at the same
exactly.
height.
Excellent. Delta H is the same in each case. So the result is delta U is going to be the same as well. So delta U is equal to mg delta H. It is the same for all since we have the same initial and final height. So if delta U is the same, let's now look at delta K. I know that W net equals minus delta U, and this is equal to delta K from chapter 7. So basically, I can deduce delta U equals minus delta K, by the way. Delta U is the same in all situations, then delta K is also the same in all situations. Now, the block was initially stationary, so K initial, I'll first deduce delta K is the same. Now, I know that the block is initially stationary, so V initial is 0, and thus K initial is 0. So delta K is going to be none other but K final itself, because K initial is 0. So K final is the same for all situations. And V is going to be also the same for all situations. So I have ranked according to the kinetic energy of the block at point B, and I have ranked according to the speed at point B. They're all the same.
This meeting is being recorded.
So I want you to notice the formula that I just used. I said W net is equal to delta K. This is chapter 7. And then now in chapter 8, I said W net is equal to minus delta U. This is for chapter 8. Well, I have to fix my terminology better. I will not write this as W net. It's actually the work done by gravity is equal to minus delta U. What I will deduce next is, if gravity, let's say, is the net force itself, then I can write delta K equals minus delta U. If I only have gravity, or if I only have an elastic spring. This equation is an important one. I'll actually isolate these two to one side. I'll show you the annotation rather than writing twice. So if delta K is equal to minus delta U, I can also write that delta K plus delta U is 0. I'll take this to the other side, and then I'll get delta K plus delta U is equal to 0. I will define the sum of these two, the change in kinetic energy and the change in potential energy, to be the change of the total energy of a system. So I will define the total mechanical energy to be the sum of kinetic plus gravitational potential energy. And one thing I can deduce is, if I only have gravity acting on the object or spring force only acting on the object, then delta E should be equal to 0. So I put a condition here. I said if all forces are conservative. What do we mean by that? I mean that if the work is done only by gravity or spring force. If I have some friction, then some energy is lost by heat. I will not say the total mechanical energy change is 0. Rather, some of the mechanical energy will be lost. So here in this slide, I essentially defined the total mechanical energy of the system to be the sum of the kinetic energy plus the potential energy. The potential energy can be either the gravitational one or the elastic potential energy. And if I don't have frictional forces, no losses, then I will say that this energy, this total energy, is conserved. U descend down, U decreases, K increases. If you go back up, then U increases, K decreases, and things look conserved actually. I will say the mechanical energy is conserved if there are no lost energies from external forces. Let me show you an example. Here, I'm studying a case of a pendulum which is oscillating or swinging back and forth, up and down. During its motion, its height is increasing and then decreasing back, and its speed will also be changing. Namely, at the maximum height, I know the speed is equal to 0. Let's take a look at each scenario. So let's say we start at point A, at figure A. We give a push to the pendulum, so we give it some kinetic energy. This kinetic energy will lift the pendulum upwards. Notice in figure B how the pendulum starts lifting up and it will go further up. In part C, it reaches a maximum height. It was here. Now it is at this height here. This is H max. Along these three situations, at first, the pendulum was vertical. It wasn't lifted up, so not lifted yet. I will say the height is 0. Once it starts moving, it will also start lifting. The height now increases a little bit, so I will have some gravitational potential energy. So notice how in my graph, I put some potential energy and a kinetic energy because the ball is still ascending, it's still moving. Now this pendulum reaches a maximum height. At the maximum height, in any motion, when we are at a maximum position, this means the speed is momentarily 0, similar to the projectile motion. So at the maximum height, the speed is 0. So I'll write K to be 0. And the height is maximum, so the potential energy is max. Look at the energy of our system. Initially, it was all kinetic. In figure C, it's now all potential. And in between the initial position and the maximum height, U and K can be intermediate. So at this intermediate location, we had both potential and kinetic energy. Now, this pendulum at the maximum height, it's not gonna just stay there, it's gonna drop back down. So notice how it drops back down here, where we will have some potential and kinetic energy again. And if it's back at its equilibrium position here, where the height is 0, it's gonna basically have kinetic energy and no potential energy now. So notice how we can basically have some exchange of energy. The total energy, by the way, is always the same.
This meeting is being recorded.
So you can see how we have some exchange. The total energy E plus K is conserved. Sometimes this energy is completely kinetic, sometimes it's completely potential. Notice how the exchange is always happening. K increases, then decreases, then increases again. It's sometimes a maximum. Notice that K is max when U is equal to 0. So I'll deduce this is when the height is 0. When the object is at a 0 height, the kinetic energy is maximum. And the other way around, U is max when K is 0, and this is usually at maximum height. So now you understand why at the maximum height the kinetic energy is 0. It's essentially because the potential energy is maximum, so the speed has to become a minimum, which is 0. E, which is K plus U, is always constant. And this is basically the conservation of energy. In problem solving, we are typically given, let's say, the initial speed. I give you the initial speed. I tell you this ball is pushed by 2 meters per second. And I tell you find the maximum height. It will be so easy. You'll just put E initial equals E at maximum height. Initially, it only had kinetic energy, so this is half m v initial squared. At the maximum height, we only have potential energy. K is 0, so I'll have mgh max. M and M go away. You'll get H max, the maximum height, is equal to what? V initial squared over 2G. I found V initial, it was given to me as 2 meters per second. And here I'll divide by 2 times 9.8. I can find the maximum height that this pendulum will reach according to the initial speed that I give it. So this will be around 0.2 meters